Hello, everyone. Thank you for joining us this afternoon. My name is Mariana Sanchez from the Marketing Department at Econtech. Today, we will talk about hydrogen estimation with artificial intelligence for quality prediction. But first, I would like to give a short overview of us. Econtech is people, passion, and performance. We develop technological solutions applied to industries in four main divisions: Smart Matrix, which are our data analytics and artificial intelligence solutions; Smart Factory 4.0, which are all our digital transformation solutions; Advanced Robotics, which are applications for cobots and industrial automation, which are PLC programming, technology updates, HMI development, SCADA, and much more. Some of our engineers have more than 25 years of experience in the steel industry. We have 2 offices in Mexico and 1 in Colombia. We have been speakers in international forums like the ISTEC and the Digital Transformation Forum. We are also Ignition certified integrators and with Universal Robots. Econtech believes in the importance of research. That is why we started our Applied Research Center in 2019. Our speaker is an active member of our research center. Maria Luisa Argaiz has a degree in mathematical engineering. She's a data scientist at Econtech, a private advisor in data analytics and data science, and a machine learning and deep learning enthusiast. We may have the participation of other members of our Applied Research Center during the Q&A. Please feel free to share your questions in the chat at any time. They will be answered at the end of the presentation. The microphone is all yours, Maria. Thank you.
Good afternoon, ladies and gentlemen. Maria, and today I'm going to talk about artificial intelligence for quality prediction through hydrogen estimation. This project is a real one case of the many applications of data science works. So let's see what the topics of the webinar are. In this presentation, we are going to talk about the steel context, some of the steel works, processes, and the problem statement in the introduction. Then we are going to talk about the project goal, which is the hydrogen prediction in the steel in the vacuum degassing process. Next, we are going to discuss the topics of machine learning, the steel processes, and how we can deploy a predictive model in the steelworks, acquiring data from several sources using a unified data platform. And finally, we will talk about the results and the conclusions. Now, let's begin with the introduction. All right, some steelworks produce steel grades under strict process control with the goal of providing chemical composition with the highest cleanliness to meet the most stringent standards required by different industries. Also, some steelworks have expensive measurement systems to control and monitor the hydrogen content in the molten steel. This kind of device is used in each heat due to internal and external requirements in the chemistry and quality. Hydrogen control is a fundamental process variable and it is required to be as low as possible, like less than 1 part per million ppm, such as FRISA, where we deploy the hydrogen prediction model. The hydrogen average is less than 1 ppm in the 95% of production. As we know, the steelworks involve several processes such as electrical furnace, EAF, ladle furnace, vacuum degasser, VD, and ingot casting, IC, among others. Talking specifically in the vacuum degassing process, the hydrogen model was developed due to the need to obtain steel for forging with low oxygen levels to reduce the long thermal treatments of the steel pieces and to avoid the appearance of flakes and cracks. Since the late 1950s, research and operational and technological innovation have been carried out on the vacuum degassing process, making possible the development of new technologies. The critical factor for decreasing the hydrogen concentration in the steel in the vacuum degassing process are time, pressure, and stirring. Reasons are that firstly, degassing time in the vacuum degassing process is since the longer the steel is under 2 millibars, the more opportunity it has to eliminate hydrogen. Second, the steel must be in motion to bring each portion of the vat into contact with the vacuum. The steel movement is carried out by argon injection in the VD. And finally, pressure. By decreasing the VD pressure, the hydrogen solubility is minimized and diffuses outwards. Through the development of this project, we have been concluding that there are other relevant operational variables to promote hydrogen elimination, such as temperature, steel chemistry, and the presence of other gases such as carbon monoxide and carbon dioxide. Now, let's talk about the problem statement. Vacuum degassing plays a fundamental role in promoting better cleanliness and quality of the manufactured steel by minimizing unwanted gases in content in the steel at the end of the vacuum degasser process is sometimes not sufficiently minimized, and this causes rework, increased time, effort, and expense in production. So there are cases where a second vacuum cycle is needed, but it generates reworks and increases production costs in such cases. What is the purpose of this project? Well, Freeza Steel Work and the Applied Research Center of Econtech collaborated to implement a machine learning predictive model that estimates the final hydrogen by analyzing the key variable for dehydrogenation. By obtaining the lowest hydrogen feasible, it is possible to have a positive effect in the areas of productivity, safety, and cost. The artificial intelligence has a low error. That means that we can save costs by avoiding reprocessing, minimizing time in operational activities in the vacuum degassing process, and allow us to make decisions respecting the estimated value. So we can generate recommendations of the best ranges of the process variable that allow the reduction of hydrogen content in the steel, increasing the quality of the manufactured steel, increasing the productivity in the VD, and reducing the energy consumptions in those processes. Additionally, to help the operator to make better decisions by displaying operational variables in the HMI. And this prediction was framed to high alloy steel. Now, we're going to get into detail about data science and machine learning. It is well known that data science aims to extract knowledge through the study and the analysis of data. Since companies have been collecting data thanks to the communication systems, data science is needed to understand the company's data. Therefore, it is possible to study the data thanks to statistics and its different types of analysis, such as descriptive, diagnostic, inferential, predictive, and prescriptive. But specifically, in the predictive analysis, we use algorithm from machine learning, which is a branch of artificial intelligence. And machine learning is the study of computer algorithms that can improve automatically through the experience and by the use of data. When running a machine learning program, it is first trained to optimize the model parameters using a large part of the entire database, called training data. Subsequently, the algorithm is tested to evaluate how well it learned in the training stage with the remaining of data. Also, machine learning has several types of learning, such as supervised learning, which can be used to predict a categorical value or a numerical value. So, when we predict a categorical value, we use a classification approach. But when we predict a numerical value, we use a regression approach. Therefore, depending on the type of learning and the machine learning algorithm, there are some metrics to evaluate the model performance. In this case, we use the mean absolute error. For those reasons, it is crucial to understand the steelworks data in order to extract knowledge from processes. Now, let's discuss the machine learning predictive model that was deployed in the steelwork. All right, data science was applied to solve the need of reason. For that, it was necessary to know the best, safe, sustainable, and efficient way to implement it in production. Therefore, we use a methodology of machine learning operations, MLOps. And the steps that MLOps suggested following. First, we properly establish the objective, hypothesis, research, and the problem that I have been talking about. Then we collect from different information a list of potential variables to be used as input to the algorithm. Next, the acquisition, collection, and storage of data quality. Those steps have been crucial as it measures how adequate a data set is to serve its specific purpose. Then we made a descriptive and diagnostic data analysis to provide an overview of how the data behaved in the past using central statistical measurements and statistical dispersion measurements. And then feature engineering. Feature engineering is the bridge that connects the raw data and the data that serves to represent the phenomenon in question. Here we use statistical methods such as probability measures, sequential feature selection, and data normalization. And the predictive analysis. Here is where we apply machine learning algorithms. Once detected the best group of features that have the most important in the hydrogen content in the steel, we start the modeling stage. The database was split by 70% for the training phase and 30% for the test phase. We randomly select the sample of each hit, ensuring that there was no train on any specific class. Then consider and evaluate more than 10 machine learning algorithms. And here the evaluation metric for the models was the mean absolute error, MAE. The model selected belongs to the supervised type. It is based on instances, so hydrogen content was estimated by local interpolation of the associated response variables of the most similar samples in the training set. And lastly, almost lastly, in the deployment, the model is available to the company. Also, we ensure that the model meets the above requirements and then is automatically implemented in production, monitored, and if necessary, errors were corrected so the model can run correctly. And lastly, model maintenance, right? Constant model maintenance became essential since input data is highly susceptible to change by the nature of the process over time. In addition, at this stage, it's essential the collection of more data, so it's possible to retrain the model to be more accurate. In addition to the fact that obtaining more data, the model is able to reduce bias and variance. Now we are going to see the unified data platform. All right, data are the building blocks for machine learning models because they are built with data, and machine learning models are data dependent. The unified data platform is an information source that is easy to configure, allow us to share information with various systems in a simple and scalable way. The unified data platform is like an available data universe, and when necessary, we can consult the data. So unified data platform is possible to acquire data from several places, such as level 1 and level 2. Therefore, by gathering information and data in one only place is possible to empower data analysis, apply data science, and develop machine learning models. The hydrogen model runs under this unified data platform, which connects it to other software to make the predictive model. So this platform helps us to visualize and make a statistical analysis like descriptive and diagnostic analysis to make decisions based on data. Now we will launch a pool and then we will discuss the results and the achievements of the project.
Thank you, Maria. Well, the first question is, have you ever applied data analytics to improve the quality of your processes? If yes or no. And the second question is, which are the top priorities of your melt shop to improve quality prediction, energy savings, failure prediction, increase productivity, or others? Thank you so much. We'll give just maybe 3 or 4 more seconds to let you answer the poll, and I will share the results. 55% said that yes, they have applied data analytics to improve the quality in their processes, and which are the top priorities are 55% said quality prediction, 45% said energy savings, 45% also said failure prediction, 36% said increased productivity, and 9% said others. Thank you so much.
All right, let's see the results. This model explains the hydrogen behavior in the 97% of the 90% of heat manufacture. It is important to highlight that the objective is that the mean absolute errors are close to zero. In this case, we can observe a mean absolute error of 0.17 for training and 0.22 for test set, while for production we can observe an of 0.21, which is adequate and valid in practical. Next, let's discuss the operative results and the conclusions. All right, once the model is deployed, operational results were the following: increase in productivity from 5 to 8%, energy savings between 3 to 4%, a reduction in sampling, a reduction of the gassing time from 2 to 3 minutes, data-driven decision-making was enabled. Additionally, it was possible to prescribe the best treatment practices that allow obtaining the desired hydrogen. The vacuum degassing process reduces the hydrogen concentration in molten steel, improving its quality. The applications of data analytics methods allow us to predict the hydrogen content in advance to actual measurements, reducing productive time and energy consumptions. Also, as a byproduct, this project results in visualization, analysis, and monitoring tool of hydrogen and other several features and signals in the vacuum degassing process, bringing a suitable just-in-time decision-making tool for operators and process engineers. That brings us to the end of the presentation. I sincerely appreciate that I've had this opportunity to present to you. It was a pleasure to be with people who is passionate about data analytics and its application in steelworks. And I'd like to summarize by saying a quote from Carly Fiorina that was changed a bit by me. The goal is to turn data into information, information into insight, and insight into action.